So that was fun. So I'd like to tell you about constraints on quantum gravity. So what I would like to tell you about is sort of general feature of low energy effective theory of quantum theory of gravity. And so this is sort of a continuation of program that Krumran-Braffa advocated like a little bit more than 10 years ago. And then we have followed up on that with some details and some new ideas around that time called Swampland question. So let me first read it. So the question is that given an effective theory of gravity, how can one judge whether it is realized as a low energy approximation to a consistent quantum theory with ultraviolet completion, such as string theory? So in the case of standard quantum field theory without gravity, the answer is that answer to this kind of question is that basically you can write down any low energy effective action as far as it is sort of internally consistent within low energy field theories, and they expect that to be UV completed. So of course there are obvious things you need to check, like absence of gauge anomalies. So that constrains the particle content of standard model of particle physics, for example. But beyond those obvious constraints, essentially you'd expect you can write anything, and then, for example, the pion theory gets completed by QCD, for example.
But also some slightly less obvious things like signs of certain coefficients, like because of causality.
Yeah, that's right. Yeah, so there are those things, indeed. Yeah, so there are some signs of higher derivative correction that can be checked. So I should admit that this is a little bit subjective thing, because, for example, one could have thought that sign of this higher derivative term is one of these Swampland constraints, but then it turns out that those can be explained within the low energy approximation. But some of what I'm going to tell you might not be of this kind. So I think that's interesting to understand. So that seems to be a special feature in some sense of quantum theory, gravitational theory, that there seems to be non-trivial constraints that so far we have not been able to explain within low energy scheme only. It requires that the existence of a constraint requires knowledge about UV completion. So I think this is an interesting thing because, well, eventually we would like to understand what string theory tells us in our low energy world. And, but of course there is a huge energy gap, and building accelerator is very hard to that energy. But if there are some hints of constraint, then you can test it. If you can test it in low energy, that would be interesting. So what I'm going to tell you today will not lead to that, but there is an indication. I'm going to present indication that there are such non-trivial constraints. And so it will be interesting, first of all, to understand what these constraints are and show the existence of these constraints, and also maybe what the origin of this constraint. For example, gravitational theory seems to have non-trivial UV-IR relation compared to other field theories. So for example, going to higher and higher energy does not necessarily go to shorter and shorter wavelengths because of the black hole and etc. So understanding those, I think, would be interesting and help us understand quantum gravity and ultimate unification better. So that's sort of motivation of what I would like to do here. So today, I would be mostly interested in discussing what kind of constraint you can give to symmetry of low energy theory. So of course, symmetry has played a very important role in physics. And so in identifying fundamental laws of nature to construct models, symmetry has been a guiding principle. But also using these laws to understand and predict the dynamics and the phases of matter. For example, in condensed matter physics, this has played a very important role. So for example, in the standard Landau paradigm of phase transition, the symmetry characterizes phases. So those have been very important both in sort of discovering laws and also using laws. But symmetry is also deceiving. So first I would like to mention that there are two types of symmetry. So if you have low energy theory, you can have gauge symmetry, or you can have global symmetry, and you can have both. But gauge symmetry is sort of deceiving in a sense that it depends on your description. So there are many known examples by now that two seemingly different microscopic Lagrangian with different gauge symmetry and different matter content can describe same physics in low energy. And so this can be the duality can be equivalent between the complete theory, like n equal 4 super Yang-Mills in an example, where you have, say, for example, gauge group SUN, n equal 4 Yang-Mills, which is totally equivalent. The Hilbert space are totally the same, operator algebra is the same, to theory with SUN over Zn. In general, if you have gauge group G and gauge group Lagrange dual to G, have the completely equivalent description. Seibach duality is for low energy description, but within low energy, you have seemingly two different theories with two different matter contents, and the gauge symmetry are equivalent. So that means that gauge symmetry is not an intrinsic property of given theory, but it depends on how we describe the theory. On the other hand, global symmetry is a well-defined concept, it seems, for given theory, because global symmetry acts non-trivially on the physical Hilbert space. So you can decompose Hilbert space in the representation of the symmetry. It acts non-trivially. So there seems to be a genuine physical presence for meaning to global symmetry. However, I'd like to argue today that in a consistent quantum theory of gravity, there is no such thing as global symmetry. So symmetry is very useful, but is also deceiving because gauge symmetry does not exist, and so the gauge symmetry is ambiguous, and global symmetry does not exist. Okay, so this has been actually a sort of long-standing law in the theory of quantum gravity. I guess when Sandeep was at Caltech, John Preskill was thinking about these questions too. And so there is actually a standard argument against global symmetry in quantum gravity. So I would like to first review it. And so this is, as I said, I'm going to say there are some holes in the argument. So I'd like to point out some of you may have other objections. That's totally fine because I'm not advocating it. And if you actually point out holes, that would strengthen my case later. So I would welcome that. So but let me just run the argument. So suppose, so this argument works for continuous symmetry, not for global symmetry, discrete symmetry. But suppose you have a continuous global symmetry G in the quantum theory of gravity. Well, so suppose for example, G is like SU2, for example. Okay, and then you must have particles or matter transforming non-trivially under G. So then you combine these matters to make black hole. So then you can imagine that you can make a black hole in arbitrarily large representation of the group. So for example, if you have a spin J representation of SU2, you have 2J plus 1 dimensional representation. So suppose we take J to be very large, extremely large. And then let the black hole to Hawking radiate, but keep mass still larger compared to the Planck mass, so we can still trust the Bekenstein-Hawking formula. Now, if G is global symmetry, then we expect Hawking radiation to be neutral in G. Now, so this is where the distinction between global symmetry and gauge symmetry appears. Because if G were gauge symmetry, and if there is a gauge boson associated to it, then there is a long-range force between charged particles. So for example, if G is U1, you have a Maxwell field. So that means that if the black hole is positively charged, it preferentially emits positively charged particle compared to negatively charged particle because there is a Coulomb repulsion. So there is sort of color to the Hawking radiation. But this does not seem to happen if you have a global symmetry. Yes? It's not a singlet of G. Oh, you mean?
How do we know that the Hawking radiation is non-uniform?
Yes. So that's a very good question.
Because the principle of the structure, you're in a gravity
Right. Indeed. So this is one of the whole of this argument, namely that, so this is assuming that Hawking radiation, so when you say G neutral, you mean the singlet, you mean the Hawking radiation, not the black hole, but Hawking radiation. So here I assume that Hawking radiation is G singlet. That's what I mean by G blind. So in the semi-classical calculation of Hawking, it's G blind, that's what I meant by this. But we know that Hawking radiation must have some subtle correlation with the microstate of black hole, because otherwise the information will be lost. We believe that, well, at least I think that one of the ways that information escapes from black hole is that there are subtle correlations in the Hawking radiation that encode the information of the particular microstate. So there can be a very subtle effect that sort of gradually leak out symmetry. But there is no long-range force for global symmetry particle with global symmetry charges. So precise mechanism seems to be a little bit hard to come up with.
I think he was asking a simpler question. It's just would there be new black hole solutions that sort of like break the region?
Oh, I see. So you're asking whether, so this assumption may be wrong, that here I assume that you still have Schwarzschild black hole.
Yes.
Namely that because of the no-hair theorem.
So maybe the black holes in the large representation of G, there's some different equation to satisfy, which is that gravity plus matter.
Okay, so actually I have to go back and check how much, so what is the context in which, what are the conditions for no-hair? Because I thought that for some certain matter theory satisfying energy condition, that the no-hair theorem is still true. Yeah.
For example, with a scalar field which carries a UN charge, you can still prove a no-hair theorem.
Right. I think for some large class of theory with certain energy condition, I need to check the literature, but still the no-hair theorem is still true, I believe.
And there are situations when it's violated, like in EDF. There are situations that
Oh, okay. Okay, but this is a potential hole in this argument. Yes, please.
This is not about this particular argument, but about this is whole region of an asymptotic symmetry and so on, where the large gate transmission part of the Vector-Morphism group, they say they are global symmetry and they
Yeah.
calculate a certain modernity. Are these also distilled out by your theorem?
Yeah, so let's discuss that later, because I will spend quite a bit of time, and in fact, the majority of my talk today on the definition of symmetry, because as you will see, once we define what symmetry means precisely, then the proof actually automatically falls on your lap. So let's discuss that at length later as we come to that. Okay? So the idea is that suppose this is true. Now you started with 2J plus 1 dimensional the black hole state. And then let it Hawking radiate, where you can certainly arrange J and the mass and the radiation in such a way that the 2J plus 1 exceed exponential of the Bekenstein Hawking entropy for that black hole. So that's a contradiction. So that is sort of the argument. Now, as Michael pointed out, there are some issue with that. And also there is a limitation. For example, this argument does not work for finite group, for example. And, but there have been some expectation that absence of global symmetry should be extended to discrete symmetry, finite group symmetry as well. So, for example, if we have Z2 symmetry, there is only one-dimensional representation. Z2 symmetry has only one-dimensional representation. So that nothing like that will be a problem. So, so what's going on? So we would like to present better proof of this. So that's a sort of purpose of this talk. In fact, there was an earlier work by Daniel Harrow 3 years ago already, which has some actually hint about how to go about deriving it. So I've been discussing with Daniel and hope to finish the paper by the end of this year. I don't want to jinx it. It's already like 90 pages ongoing, but we'll see. So what I would like to, mainly I would like to talk about this, and then there are some additional things that I can mention. But the main thing is that any global symmetry in anti-theta space, the gravitational theory in anti-theta space. So I'm going to discuss this in the context of ADS-CFT correspondence, where we know the precise UV definition of gravitational theory, and then it's inconsistent with locality of conformal field theory. So that's what I would like to discuss. Now, so before I do that, as I said to Ronald, that we need to have precise definition of symmetry. So I first would like to define what we mean by global symmetry. And by the way, since I'm going to sort of talk about global symmetry both in gravitational theory in ADS, and also later, if I have time, also global symmetry in conformal field theory and its relation to gauge symmetry in the bulk. So I'd like to define, so the definition of global symmetry that I'm going to define use here should be applicable for both ADS side and CFT side. Now, ADS side, there is some subtlety to it, because I would like to, as you see later, that I would like to implement some locality assumption. And the notion of locality in gravitational theory is subtle. And so I would like to have a little bit of footnote on that, and I'll be happy to expand the footnote into some discussion also here. But so I would like to sort of warn this point. So let's discuss global symmetry. So this is how we learn, or at least how I would teach in undergraduate quantum mechanics course. So we say that quantum mechanical system has global symmetry G if for every element small g of the group, so there is a unitary operator U of G acting on the Hilbert space in such a way that it makes representation, and then it commute with this action commute with Hamiltonian. So that's sort of definition. Okay. There is a possibility that there is a projective representation with phases. So in fact, I'm not going to talk about that because that Michael will miss the plane if I do that. But we have some generalization of that with projective representation, and also cases with spontaneous symmetry breaking and etc. But I'm not going to discuss that today. But this definition is good as symmetry, but there are cases. But in fact, I should say that we are not able to prove the theorem that there is no global symmetry if we use this definition. Well, and because there are symmetries that sort of are not really local, and we are going to use locality of the symmetry in sort of intrinsic way. So for example, suppose you have a Hamiltonian, and if you look at 40-second eigenstate, well, it should be 40-second eigenstate, and then you just rotate that eigenstate. That clearly satisfies all of these conditions. But so that symmetry should exist in any theory, but I'm not able to exclude that. So I'd like to add one more condition to this to implement the locality. So first three conditions should be obvious, I hope. So symmetry. Since we are talking about quantum field theory, so in the gravitational case in ADS, it's a little bit subtle, but you have sort of approximate local operator with gravitational dressing, and the size of the dressing is of Planck length. And so we are going to put constraint on low energy effective theory. So within the Planck length size, we treat that as a local operator. So yeah.
Is it Planck scale dressing, or is it the kind of analog of the Wilson?
Yeah. So there is a gravitational Wilson line connected to the boundary, but I assume that Wilson line, that in the case of gravitational Wilson lines that commute with such a symmetry operator. So there are some assumptions about that. So I assume that there is such a in the case of ADS, we also can define approximately local operator with gravitational dressing connected to the boundary. But this part is sort of neutral under G symmetry, which I think is reasonable. So with this assumption, you assume that you have this symmetry operator U of G, like this one. And then this, if you conjugate any local operator with U of G, it maps to the same local operator at that point. So symmetry, I should say, because of this, symmetry I'm going to discuss it does not include space-time symmetry, like ADS isometry or parity or time reversal. We can extend this to those cases, but those are, so in the case of gravitational theory, these are sort of mixed up with the diffeomorphism symmetry. So here, let me just discuss the internal symmetry in the sense that it is mapped to local operator at the same point. And then it should be faithful on the set of all local operators. So this is actually this point is becoming very important, especially when we discuss dualities and other things, because in those cases we need to understand precisely what the symmetry group is. So sometimes, for example, there is you have to make a distinction between SU2 and SO3, for example. So if you have SU2 group, but you only have a local operator with integer charges, it's more proper to say that symmetry group is SO3. So that's sort of, I hope that's it.
Faithful means that there's no generator that acts trivially in all of them.
Right, yeah, that's right, yeah. And also it should commute with energy momentum tensor. So I hope these three assumptions are obvious to all of you. Yes, that's true. So this third assumption may not be necessary. Now, but it should commute with Hamiltonian. Now, so yes. Yes, please. Yes, please.
So the statement that you made with Carlo is on the CFT side.
We are going to make statement in gravitational side. That so if we assume such thing exists in gravitational theory ADS,
Yes.
there is a contradiction.
Right. But the contradiction was the absence of locality on the CFT side.
Absent of locality in the gravitational side.
Oh, okay.
Because I'm going to, what I would like to show is that in ADS gravitational theory, there is no such thing as global symmetry satisfying these conditions.
Okay. So I don't have to worry. Okay. Just go ahead.
Yes,
The question will come up.
right. Yeah, so we will see how I'm going to use it.
Hiroshi, why are you insisting on one? Why is one necessary?
Well, without one, I don't know how to prove it, but that's the sort of real reason. Because, for example, this would not satisfy this condition. So we wanted to exclude these examples. So finally, we need one more ingredient in proving it. And so this is something that actually people in algebraic quantum field theory have sort of utilized it with great effect. And so this is an idea of generalization. You have a question?
One also includes the rotation.
No.
So you have local operators, local operators.
Yeah, but if you have local operator at other point, it won't work, right? So this should work for local operator in everywhere. So the Neta theorem. So we'd like to have a sort of Neta theorem in proving it. Well, if in ordinary global continuous symmetry, you have a Neta theorem. But in fact, I'm going to argue that Neta theorem is actually not true even in continuous symmetry in general. And I can show you counterexample to that. But also we would like to have generalized this type of result to discrete symmetry, the finite group symmetry. So there is no Neta theorem for finite groups. But people in algebraic quantum field theory have actually thought about that, evidently. And there is actually a beautiful discrete version, generalization of Neta theorem that is applicable even to discrete symmetry. And cases where Neta current does not exist in continuous theory. So here is one. So since this is formulated by algebraic quantum field theory, so please bear with me that it's a little bit long. So suppose you have, so let me draw some kind of Cauchy surface. So there is a time. And then there is a Cauchy surface. So suppose you have sort of this type of picture. And then suppose you have some region here, R. So subset, subregion R. So then the assumption is that associated to this region, there is a still unitary operator U of G and R. in such a way that when you consider, so suppose this region contains point x, for operator belonging to this point, this operator acts just as if it is the global symmetry operator.
So like you flip all the spins in that region.
Yeah, that's right. So if you use lattice formulation, then you flip spins inside and then not doing anything outside. So that's sort of the kind of thing. Okay. So this is sort of formalizing this. So so this satisfies all these conditions and on the space of local operator. So clearly, if Noether theorem is true, then 1, 2, 3 would imply 4. Because if Noether theorem is true, then what you can do is that where you have a Noether current, so U of G is expressible as exponential of transformation, the amount of transformation times J naught integrated over sigma. But sigma can be divided into R and its complement. So you can just divide this integration region into that. So then you can write this as e to the I theta of J0 integrated over R and e to the I theta J0 integrated over its complement. I apologize that people watching this video, it may be hard to read this detail. But you can see that you can have product structure. So in particular, you can define this as exponential of integral of Noether charge density, Noether charge density for integration over R only. Right? So if you have Noether theorem, it holds. But the nice thing about this requirement is that you can also require that for discrete symmetry. And so this is more technical than these three. So it would be nice if we can get rid of this condition. And in fact, what Shiraz says is essentially that point. Namely, that if you can have some kind of splitting of the Hilbert space between with those associated to this region and those associated to complement, then this is actually true. So this is related to what actually Sandeep has been studying with Ronak for some time, and so maybe we'll have discussion on that subject also. So I'd like to, so because of that, I have actually prepared a few slides. So let's discuss that. So there is actually a very nice paper. These are direct quantum field theories in fact, in late 80s, that if quantum field theory satisfies what they call split property, then this 1, 2, 3 implies 4. Okay. So namely that, so this is actually sort of idea of the proof is not very hard. So what this is, so in the sort of a caricature of finite dimensional picture, what it says is that suppose you have a Hilbert space. Suppose you have a Hilbert space and suppose it decomposes into tensor product. And suppose you have a unitary operator acting on it. But if it is acting on it in such a way that if you have any operator acting non-trivially on 1 and trivially on 2, and then if U O1, U inverse is always always can be written as operator acting only on U1, and then the same applies to U2, then you can show that this U is equal to tensor product of U1 and U2. So namely that if the Hilbert space split, and if there is a local operator like that, the symmetry acts locally, this is sort of finite dimensional version of locality assumption, then 4 works. So that is sort of basic idea of the proof. Now, so that seems to be a good news because we often say that if the Hilbert Cauchy surface decomposed into 2 segments like that, then the Hilbert space splits into 2. Okay, so if you are happy with this, there is nothing. So there is nothing more I should say. So I can skip the next 3 slides or so. But because, I mean, Sandeep spent quite a bit of time sort of studying this related question, so I have added a few more slides to expand on this. And in fact, this is actually not as trivial as you may think. So of course, if you, as Shiraz says, that if you start with lattice formulation and split, then at that level you can split the lattice, and obviously it's true. But if you take sort of continuum limit and then think of this in terms of quantum field theory, it's less obvious. For example, if this were true genuinely, then if you compute the entanglement entropy for region R1, then UV divergence could be dependent on what kind of state you consider. But this is, I mean, we would expect UV divergence of entanglement entropy to be universal. So there's something that to be clarified for this kind of property. So formalization of this is called the split property. And in fact, I'm gaining more respect for these people than before because some of what they did is quite actually interesting and non-trivial. And in fact, Ed Witten wrote a very nice 78-page lecture note on this subject. And he told me that this is what he was actually going to talk about at Strings Conference this year.
What do you mean? It is already true that UV divergence isn't universal. It depends on the state you take, right? You take a high level state with volume divergence and so on.
Right.
So what are you trying to say with the last segment?
Sorry? Yeah. So what I mean that within a low energy world, this is not true. And this is where we want to prove theorem. So that's why.
Oh, you're saying for all low energy states because crystal always have the same area term?
Yeah. Right. Yeah. So in fact, I'm going to give you counter example to split quantum field theory with split property.
Yeah, I didn't understand the comment. So volume terms are again higher. You took the UV cutoff.
So but you have to get to very high energy of UV scale, UV cutoff scale. So that's why it works for lattice. For example, if you have a lattice model, then it seems like a Hilbert space split. But the way that it's split is that but that is consistent with this because this UV depend so non-universality of UV divergence is regained by considering state close to UV cutoff. So.
And then your point is in the continuum limit, the splitting gets more subtle.
Yeah, that's right. But there is actually a thing that replaces this split property. So this is actually formulated by algebraic quantum field theorists. So let me first state it. And again, but done by algebraic quantum field theorists, so it's a little bit long, but let me try to unpack it. So they say that quantum field theory on Cauchy surface sigma has a split property if there is a type 1 factor n. So let me first tell you what type 1 factor is. So this is actually some special type of von Neumann algebra. So I hope that von Neumann algebra is not something that is so scary. The name factor can be scary, but what it means is that it's a von Neumann algebra, but its center is trivial. So it doesn't contain any sort of trivial center. Okay? And then what you say is that suppose you have a region R in the Cauchy surface, and suppose you have a slightly larger region R prime, then there is always some, it's clear that algebra of local operator over here is smaller than operator. So if you expand the region, it's clear that the algebra of local operator becomes bigger. So the split property means that there is something in between them, which is type 1. So that is sort of, so why do I have to say that? The reason is that type 1, if you have a type 1 algebra, then it realizes nicely on the Hilbert space. So there is a Hilbert space realization of type 1. So type 1 is here. So so no center, and there is also some property called minimal projection, but this is essentially the important point. And then the problem is that this one in general is not that there are lots of evidence to show that A of R is not nice thing. And in fact, this is what they call type 3. And so if this was a nice thing, you could have said that, well, you have split property by just a representation of this von Neumann algebra or something. But it doesn't quite work because algebra of local operator is not type 1. So therefore, this n thing, the type 1 algebra in between, is a factor is next best thing you can do. Because what it means is that if you sort of expand the region slightly, then there is something in between. In between the algebra of local operator here and the algebra of local operator here, that has nice representation in Hilbert space. So so type 1 factor can always be realized as a set of all operators on some Hilbert space. So you can therefore sort of approximately think that this Hilbert space is so what we wanted to say was that we wanted to see was that suppose you have a Cauchy surface and suppose you have a region R here, then there is some kind of Hilbert space associated to it for this region. And so since A of R is not type 1, there is not really such a thing. But the Hilbert space which realizes n is almost like that.
It's smoothing out the hard cutoff.
Yeah, that's right. It's sort of formalization of this. Yes.
And this is a statement about one-free table, right? But there would presumably be subtleties in the theory of gravity.
Yeah, so these are subtleties that I was talking about of Planck scale. But so we are talking about the low energy theory in gravitational side. So
You spent quite some time arguing that the algebra in fact doesn't exist.
Sorry?
The algebra is not true if you restrict to a factor. If you restrict to a particular
so A of R has genuine definition.
in the theory of
Yeah,
gravity.
yeah. Well, in theory, no, you're talking about theory of gravity.
Yeah.
Okay, so that exists only in approximate sense. Yeah, locality is a program, so it only exists in approximate sense.
But sorry, when you just go back, the obstruction to A of R being nice in this sense, if you try to have a sharp cut,
Right.
is it a non-trivial center in some sense or more than that?
I'm going to give you an example of this. So actually, I'm going to show you an example of quantum field theory with non-trivial center appearing, and then causes a problem. So we'll see. So okay, so here is actually an example. So in fact, actually, if you ask algebraic people, algebraic quantum field theory people, then they say that they believe that this property is true for any quantum field theory on flat Minkowski space, RD. And in fact, there are no known counterexample to this split property. But if you consider non-trivial topology, then there are actually examples. Interestingly, people in algebraic quantum field theory have not thought more about these kind of non-trivial geometry. So this seems to be something new. So this is kind of interesting. So here is actually one of the examples, which actually maybe related to what Sandeep and Ronak did, because this is actually about free Maxwell theory. So suppose you consider free Maxwell theory on S1 times sphere as a Cauchy surface, times time direction. So here is a caricature. So you have a SD minus 2 and S1. So this is your Cauchy surface. So suppose I choose your region R to be this kind of band. It wraps this sphere and extends in some finite segment in the S1 direction. Okay, so now I'm going to argue that this pure Maxwell theory is not split. So the reason is very simple. So suppose you have a flux operator associated to this region, associated to this S1. So this is a genuine operator. But you see that since flux is conserved in pure Maxwell theory, so you can move this flux away from this region. So that means that this flux commutes with every operator in R. So this is in center. But and you can move this back in. So that means that this N contains non-trivial center. So this is sort of a counterexample to the split property. And in fact, this is closely probably related to what you were discussing in your paper, because there also the issue was about how to deal with flux coming out from this region, etc. So you see that this what algebraic people are doing is very actually close to what you are worried about. And so there is actually a related issue, which is actually the reason. So I'm coming back to the original point of constructing generalization of Noether theorem. So in fact, in this example, the Noether theorem does not exist in the following case. So suppose you consider product of pure Maxwell theory. So suppose you have two Maxwell theory without charge. So without charge, so the symmetry group, the gauge group is actually R times R, non-compact group. So you have two Maxwell theories. So the Lagrangian is sum of F1 square plus F2 square. So there is a rotation symmetry mixing these two. So since this is a continuous symmetry of field theory, so you would think that there is a Noether theorem associated with it. So I challenge you to construct Noether current. And if you construct Noether current for this, you find that it's actually not gauge invariant. So there is no gauge invariant Noether current. You can try to remedy that, but then you get into other program. In a flat space, you can still sort of make sort of remedy to it, and then construct some kind of local symmetry operator to it. And because it is sort of split in flat space. But if you consider non-trivial topology, you will encounter that there is a problem with Noether theorem.
Without charge, we don't want quantization of flux.
Without charge, well, so basically it gets into problem. So actually Noether current associated to this is something like this. So J mu is like epsilon of so in 4 dimension, for example, mu nu rho C. So it's like something like A mu I F J of mu nu with epsilon or something. So this is sort of so the problem happens when you consider some flux background. So then there's the gauge symmetry does not. So the thing is that this is not gauge invariant, but charge exists, because under gauge transformation. So if you do gauge transformation, then J mu changes by something like total derivative of lambda and F mu nu or something. And so if this decays sufficiently fastly, then it's okay. But if there are flux emanating away from some region, there is a problem. So it's again very close to what Sandeep was worried about. So you see that there is a close relation between the split property and the existence and non-existence of Noether current.
If the flux is quantized, then you can't rotate them.
Yeah. Okay. Oh, I'm sorry. So you're worried about you're talking about the case when gauge symmetry is not R cross R. Yeah. So even there is a problem, in fact, because what happens is that indeed in that case there is no O2 symmetry. But suppose you have 2U1 with same radius, there is a G2 symmetry exchanging to it. So then you can ask, well, does this still satisfy this generalized Noether theorem? And it's not. It's false. So that was that's the answer to your question. So even in U1 cross U1 case, even though there is a G2 symmetry, but this generalized Noether theorem is false in that case. So again, it's because this theory is not split. Okay. So but we conjecture that it's always possible because of the intuition, essentially, that Shiraz says that you can always do it in lattice. So you can always add some UV degrees of freedom to repair the problem. For example, in the case of Maxwell theory, you can arrange so that the Maxwell theory appears as a sort of emergent symmetry in low energy. You can start with like CP1 model or something like that in high energy, and then in low energy you can have approximate gauge theory. So in that case, the theory is split. So I think that's probably the case, and so this is what I'm going to assume in the rest of my talks, that the theory can be split, and therefore this fourth assumption holds. Now, in fact, if I mean, we have time. I can also tell you a proof without using this assumption. And but for the purpose of presentation, let me assume that. So let me recap. So what I was telling you about is that the quantum field theory has a split property. If there is a type 1 factor, which is a von Neumann algebra of trivial center in this kind of nested configuration. And if you assume this, then this generalization of Noether theorem holds. So this is what I'm going to assume. As I said, we do not need this type of assumption. We do not need to assume for to prove the result. There is an alternative proof, but let me just assume this for now. Okay, is there any questions so far?
Just to say that I have to absorb what you said, but for example, if you try to split the Hilbert space for a H-wave by putting it on the lattice, you do get a split Hilbert space, but you still get a non-trivial center.
Right.
And so the algebra N that you're referring to, I have to think about what it is, because there is a trivial center sort of consistent with some way of
Right.
split it.
Right. Yeah. So I haven't thought completely through what happens in that case, but I would be happy to discuss with you more. Okay. So now it comes to the derivation of this. So as I said, I'm going to prove this in the context of ADS-CFT correspondence. So I'm going to say that if you assume such symmetry, global symmetry exists in ADS, it contradicts with ADS-CFT correspondence. And so I'm going to use what is called entanglement wedge reconstruction or subregion duality, where not only local operator in ADS can be realized as operator on the boundary, but if that operator is located in some particular region in the space in ADS, which can be sandwiched between Ryu Takayanagi surface and the boundary region, then you can actually realize this operator in the algebra of operator in this associated to this region. So this is called the subregion duality. So this was started out with the work by Hamilton, Cabot, Lifshitz, and maybe some of the earlier work, where they try to understand precisely how to sort of reconstruct this local operator from boundary point of view, and sort of greatly sort of deepened by the work of Papadodimas and Raju and many other people. And then, but in particular, recent work by Haro and collaborators sort of connected it to some interesting property of quantum information theory, so which we would like to use, I will use today. So let me restate it. So this is so let me restate this idea of subregion duality. So suppose we consider this ADS-CFT correspondence. So you have a conformal field theory defined on the boundary, dual to gravitational theory in the bulk. So suppose you choose some subregion A, and then associated to that there is a Ryu Takayanagi surface, which I denoted as RT. So then there is a region sandwiched between them, which is called the entanglement wedge. In fact, to be precise, the entanglement wedge is extension of that in time direction with domain of dependence, etc. But I'm just drawing spatial slice of this. So the claim is that the quantum gravity operator localized in this shaded region. So I assume that this region is much bigger than the Planck length, so that what we mean by operator localized here is not ambiguous. Then the operator localized in the shaded region can be represented by operator acting on the subregion A only. So this is called subregion duality statement. This led to various paradoxes, which led to deepening of understanding of this correspondence. So there are two paradoxes, reconstruction paradoxes. One is that if you pick a point in the bulk, there can be multiple ways of representing this point in the subregion duality. Because, for example, you can have this point can be in this blue region, or this point can be in the red region. So that means that the same local operator in the bulk can have multitude of representation as operator in the boundary CFT. There is also a problem like this here. So suppose you have an operator located in here, and suppose you divide the boundary into 4 segments like this. So then the entanglement wedge for this region is only covers this region, this covers only this region, this region, this region. None of this covers this region. So that means that any operator here would commute with all the operator here, all the operator here, all the operator here, and all the operator here. So there is actually a theorem in algebraic quantum field theory, Lee-Schroeder theorem essentially, that says that such operator should be trivial. So there are 2 paradoxes. One says that the local operator has multitude of representation. And the second paradox says that such operator is trivial, proportional to identity. And it certainly cannot be the case that identity can be expressed as a multitude of different operators. So there is something wrong with this understanding. So this is sort of a paradox. And this paradox was beautifully resolved by the work of Haley, Dong, and Harrow, and also a longer paper by Harrow, which sort of explained it in detail. And so the idea is that this type of local excitation clearly makes sense only in the low energy picture. As Abhijit has been worried about it and expressed that for a few times already, that so there is no such thing as a genuine local operator in quantum field theory. So when we talk about local operator, we are always talking about it in the context of low energy theory. So there is some small subspace of the Hilbert space of gravitational theory in which we are talking about. So this certainly is not a property of the full Hilbert space, but this is a property of some special subspace for the Hilbert space of conformal field theory on the boundary. So you have a full conformal field theory Hilbert space. In it, there is some special subspace that describes the geometric solution to Einstein equation and local excitation to it, either by excitation of the metric or excitation of the matter field. So those are the subspace of the Hilbert space we are talking about. And this paradoxical property indeed the paradoxes assume that this holds in the full Hilbert space. But if you know that this is only property of subspace of Hilbert space, then it's actually not a paradox, but it's actually exhibiting some non-trivial entanglement of the boundary theory for the class of excitation that we are talking about. So in fact, one of the interesting insights of this paper is that the entanglement property of this locally excited state in the bulk is exactly those that have been used for quantum error correction. So namely that so in quantum error correction, what you do is that you start with some Hilbert space, which is supposed to encode some information that you want to send, and then you consider many tensor product of these Hilbert spaces, and you consider some particularly entangled state on this Hilbert space, which carries the information about state in the original Hilbert space. And then you send it, and then some of the information can get corrupted, but there is unitary operators. If you know that information of which factor is corrupted, then you can construct unitary operator to get back to the original thing. So that is a quantum error correcting code property. And then the idea is that if you divide the Hilbert space into those associated to this subregion, assuming this approximate split property holds, then the way that this state, this locally excited state exactly have this kind of property, that this information is shared by these regions, but not by single region. So the thing about quantum error correcting code is that if you destroy any one of these Hilbert spaces, you still have that information. That's why you have this kind of funny property here. So, and then also, the other same thing is that you cannot reconstruct information about any information about this state if you only look at this one, this subspace. that's why sort of we have this kind of paradoxical property. Because here I was assuming that information about this can be reconstructed by this alone, or this alone, or this alone, or this alone. And so since this information about this is extended as entanglement information about entire region, so you can only reconstruct it if you actually know combination of this information. So that was sort of a nice resolution to this. So let me assume this, and then going to sort of prove what I wanted to prove. Yes.
So is there some actual model of a DSCFT where one can do explicit calculations to see these?
So yeah, so indeed this whole story started out with this work by Hamilton, Cabot, and Lifshitz, where they constructed this local operator explicitly in the case of Einstein gravity coupled to finite in the bulk. And then people started to realize that this construction has this peculiar property. And that has led to this understanding.
Because I thought when Harlow came here and gave talks here, he had this idea of whole subspaces and
Yes.
we say there, and he said that there are examples of spin chains and such like simple theories,
Yeah.
not in quantum field theories which actually appear in the
Well, so that's a toy model. That's what he called toy model of this kind of thing. So what he was doing was that, I presume I know what he was talking about. So what he was doing was that explaining actually the quantum error corrective code that these quantum information people actually uses, and then reinterpreted it in this language. So that actually is not any sort of particular example of holographic duality where you actually have smooth holographic dual, because I think the example he had was like a Hilbert space with 3 states or something like that, Q-trit or something. And but that sort of nicely encapsulates this property.
The understanding is qualitative.
Yeah. But so his point was that so you have a Q-triplet example, so that exemplify this, but that exact example exactly has this kind of property. So he was just drawing analogy with this kind of finite dimensional example.
So, just a comment. This stuff you can actually calculate using SQL and all that. He needed those tensor networks and other toy models to make other things besides like entanglement and reconstruction, which basically this part is completely precise.
So what part is that? I mean, that he can show that there is entanglement of this sort. How can you show that?
No, it is the fact that this paradox exists.
So the paradox with the resolution. Resolution is what?
I mean, I think the spirit is that you should be able to reconstruct from these different regions. And then what he does is just construct a small model which has these features. Now, of course, that exact way it won't be implemented, but
Right.
there must be some similar.
Yes, that's what you.
So there's no quantitative within the area. That's what
No. So I think all he was doing there is that to demonstrate an example in which this is not a paradox at all.
So there's no real paradox.
So he was showing that there is no paradox if you assume that this is what is happening.
Right.
So then he gave a pathway to what is happening. Okay, but in fact in his paper he actually gave a proof that if there is any resolution at all, it has to be this. Namely, he showed that if either Liu-Takayanagi formula is correct, or the subregion duality is correct, then the resolution has to be of this type. I think there was a theorem in his paper to this effect. Yeah.
And he came to that in the last of his talks.
But the thing that would be really satisfying would be to understand the detailed entanglement structure of a ground state of a real conformity.
Right. Yeah. So that's not so it has not been shown that is happening in the actual example. But what is shown is that if there is consistency at all, then the resolution has to be this. Thank you for helping to clarify this here. So now here is a proof. So I'm going to show you that the global symmetry in ADS is inconsistent with local structure in CFT. So now, since we have spent more than an hour explaining what symmetry is, the proof is one page. So, so if gravitational theory in ADS has global symmetry G, so that means that it has satisfied all these properties. And in particular, there must be a bulk local operator that transforms faithfully into another local operator at the same point. Okay? So now let's put this operator in here. So suppose you have a generalized Noether theorem. So suppose you divide the boundary into this 8 segment, and then you represented it in this way. So then, so suppose you put this local operator in here. This operator would commute with operator in this segment, commute with this segment, commute with this segment, commute with this segment, etc. So that means that this local operator should commute with this symmetry generator, which satisfies generalized Noether theorem. But this contradicts with this assumption. So that's a contradiction. So therefore, there is no such thing. So that's a proof. Any question?
So what is failing here is the faithfulness.
Yes, so that's true. Yes, so that what is failing is faithfulness. Yes. So if there is a some element of G which acts trivially on any local operator, then it's not a contradiction. But it can be applied to any element of G. So that means that entire group should be acting trivially, right? So then what's the point of saying? So okay, so you can certainly say that well we have a quantum gravity theory with global symmetry G, but too bad it acts trivially on everything, right? So you can certainly say that type 2 superstring on case compactified on K3 has a monster group symmetry and.
We wanted to show that there is a global symmetry element that commutes with every local.
That's right.
You show that it commutes with this operator. But what about every operator?
Can't we repeat this to every operator?
Well, can't you put the operator inside? You say make that smaller and smaller.
So what do you mean?
Suppose I take my operator and put it inside one of these.
But I'm free to put this over here, right?
But I thought we wanted for every local operator.
Oh, okay. So what I can do is that suppose you move it over here, I can cut the boundary to smaller segments.
Yeah, I mean, more and more segments would.
It's an identical operator. So the same operator U of G has multitude of representations, and I can cut it as small as possible. So you can move it towards the boundary. I can move it. I can divide the subregion to be smaller, and then so. Right.
But the point is this whole entanglement with deconstruction business or whatever, subregion duality, it's a duality statement, right?
Yes.
So how do you know that when you look at the entire Hilbert space?
No, I cannot. I'm not making that claim. Yeah. So this is the same. This is what I'm saying is that if you have consistent quantum theory of gravity, then its low energy theory does not have global symmetry. It should be broken. In various ways, it can be broken by some higher derivative correction to low energy theory with finite number of higher derivatives, but it should be broken in some way.
Oh, you're saying the UV theory can have as much global symmetry as it wants, but once you go to the IR, it's much global.
Well, I'm not making a statement about UV theory. So yeah. So all I'm saying is that because this is only statement about local excitation of gravitational. Sorry? Yeah. So this is an implicit assumption here. So suppose you have a global symmetry in the bulk, then it should also be global symmetry on the boundary CFT because any so there is a correspondence. So therefore, so you can so yeah, that's right. So if you have a global symmetry in the gravitational theory in G, then it should so you can that for example particular U of G, the symmetry generator should act on the boundary theory also.
So suppose I apply this to the global path of a gauge symmetry in the bulk.
Global part, yeah. So that's a different thing.
Because you need a Wilson line.
Yeah. So I have a slide to that effect later. Probably I forgot whether I put it in here this time, but indeed. So So there is a reason. So the Shiraz was mentioned. I'm not sure whether do I have a slide on. Yeah, I have a slide on that. Yeah. So sorry, say it again. So you're worried about the case. Let me try to understand. So are you worried about the case when global symmetry gets mixed with the gauge symmetry? Or? Sorry?
That the boundary global symmetry is actually gauge symmetry from the perspective of the model.
He's worrying about the usual stuff. In usual ADS CFT, you have global symmetries on the boundary which become gauged in the boundary. And that is not ruled out there. So he's trying to ask, can it be that the global symmetry of the boundary that stays a global symmetry? We know that the other thing is not coupled.
Right.
Which is part of what we
Yeah.
So that's
So gauge symmetry can exist in the bulk. The global symmetry cannot. So this applies to discrete symmetry as well. So I forgot to mention. So nice thing about this argument is that this is true whether it's continuous symmetry or discrete symmetry, as far as you assume this generalized meta theorem. Sorry? Right, yeah, that's right. Yeah, so that was sort of nice, the feature that I like about this argument.
Hiroshi, just to say, our deadlines are very soft. 115, 120 is fine.
Okay. Yeah, good.
Sorry, just to understand, so the point
You are very strict. Okay.
Sorry, just to understand, so the point is that the operator at X can be reconstructed from the boundary if we combine various regions, because then the entanglement wedge will extend all the way.
Right.
But in each individual region, you only reconstruct the shaded parts.
That's right.
And then if you have the local operator acting on the shaded parts, it will therefore.
That's right.
And then the point is that because he's assumed that the symmetry acts piece by piece. Yes.
Yeah, so the thing is that symmetry operator does not change the entanglement feature. That's a problem. That is a problem. So Neta theorem says that symmetry operator cannot change the entanglement feature of the state. And such thing can commute with local operator.
So the exact, so the operator here will instance, which for the phi of x are restricted to what you call the pole subspace, is it?
Yes.
That is what comes into your.
Yeah, that's right.
so all the discussions that is necessary for this is the discussion is quantitative. So previously the questions that I was asking about these considerations being applied to zero gravity are not necessary here. This argument is purely for the boundary consistency.
No, well, the definition of symmetry is applied to the bulk gravitational theory. We're talking about global symmetry in gravitational theory.
Right, but you are saying that global symmetry is a global symmetry on the boundary, and that's the
Yeah. So right. Yeah. Some of the property. So I have used assumption about symmetry freely for both bulk and boundary. Some of the assumptions are used for bulk, some are used on the boundary.
See, there are always operators on the
R is also region to the boundary.
bulk. Oh,
Yeah, R is the region in the boundary.
But no, the great things are at the bulk. Sure. There are always operators, but you know.
The argument when combined with the entanglement, eventually the only necessary argument is on the boundary.
The
only operators in the light region transform trivially under the symmetry.
Right.
Then there's no contradiction. But basically, symmetry using.
As small as so what is you end up proving is that almost for almost all the region in here, except for this kind of tiny region on the boundary in the UV cutoff scale, everything commutes.
And sorry, Hiroshi, just to understand this in the context of bulk reconstruction, you can create a bulk excitation, therefore, at X, and can that be represented as a excitation in the tensor in the tensor product of all the regions?
Yeah. So for example, excitation here can be realized maybe some region like here because it covers it. Electromagnetic surface covers it.
Yeah.
So yes.
Oh, sorry. So somehow that is possible, but the action of the unitary operators in
Right.
circles like that, would not agree with the action in the bound.
That's right. Yeah, yeah, yeah. So that's a contradiction. Right. Well, another thing I wanted to say that, for example, this kind of construction allows this operator to have a little bit of size. Like, for example, even if you have a Planck scale size, you can take this region to be small. Or even, maybe you can even allow the possibility that the charged state is a black hole. Because, but you can have then Hiroshi radius. But then again, if you take the boundary segment to be, each of the boundary segment to be smaller than, as small as you like, then you can stay away from the horizon of the black hole. Mute.
So often, I don't know about what happens in restriction to force and but often you have to put some sort of Wilson line to the boundary.
For gauge symmetry, gauge charge.
Even for
Yeah, yeah. Well, so as I said, I'm assuming that gravitational dressing is charge neutral.
There's still some operator. Right?
Sorry?
There's still some operator.
There is some operator constructed out of metric, which I assume to be neutral under global symmetry.
The idea is that it just connects
Oh, it
due to
commutes
mass.
Yeah, yeah, yeah.
It's like the thing, which carries
Yeah,
the
maybe
charge.
so let me go on to this discussion because this is related. So this issue has come up many times. So on the other hand, we know that so conversely, global symmetry in conformal field theory correspond to gauge symmetry in the bulk. And so that means that you should be able to have a local operator here which transforms non-trivial. So how would that work? The way it works is that if you have a gauge charge here, then you can't just have gauge charge. In order to make this to be well defined, you have to have Wilson line attached to it to make it neutral. But then with this Wilson line, the other end of the Wilson line has to end somewhere. So it's end on the boundary. But then if it ends on the boundary, then it's sensitive to any one of these regions. So therefore, this local charge excitation with Wilson line attached commute non-trivially with symmetry
It's
generated.
possible for Wilson line to escape inside a black hole if the black hole is inside.
Yeah, so you can have but you can have a pair of. If you have a black hole with a Wilson line included in it, then you have a charged black hole.
Yeah.
So then, of course, you can have a pair of charges over here.
Yeah.
But if you have a pair of charges, then it's commute with the global symmetry generator. So now there are other things that I want we were able to derive. For example, if you have gauge group G, then every finite dimensional group. Yep.
Very sorry, Mr. But
Yes,
I
please.
think the thing still is that somehow to define the concept of a global symmetry precisely, we had to put in the notion of locality. And
Right.
that notion is, of course, approximate in
Yes.
gravity.
Yes.
So, in a sense, I worry whether our conclusion also, therefore, is that in the low energy gravity sector, we don't have a global symmetry. But since that notion of low energy itself is not very precise,
Right.
localities, I worry that perhaps the conclusion may not be totally precise.
Right. Yeah. Yeah. So this is sort of coming from my original motivation of Swampland question. We wanted to make statement about low energy theory. So this is sort of fits the purpose. But if you want to have precise statement about gravitational theory, then I don't even know how to formulate it because so we don't expect the full UV quantum gravity theory to be local at all. So I mean it's most likely that for example you can have a string or you can have whatever loop quantum gravity or lattice gravitational theory or whatever. So there, I mean, any one of these assumptions that I made over here would be applicable. So I'm not claiming to make, so it's certainly an interesting question to ask, well, so can you make any statement about global symmetry in the gravitational theory? But you need to first define it. Yes, somebody is asking question. Yes, please.
Another question.
Yes.
I mean, maybe there was this discussion already. I think maybe Abhijit was raising similar things I couldn't follow at all. But the fact that the low energy quantum field theory is a gravitational theory and that it doesn't have a local energy momentum tensor, does
Well, let's see. So let me try to sort of discuss that. So certainly we are considering the situation where the bulk gravitational theory is described by Einstein gravity coupled to finite number matter field. So I'm assuming that the bulk gravitational theory is of this type. So these are certainly quantum. So these are certainly field theory. You can have energy momentum tensor. It just commute. It just is being trivial. It acts trivially on the Hilbert space by the gauge constraint. So I don't think there is anything wrong with the assumption we made and the way we use it, except that condition 3 becomes trivial because the energy momentum tensor. So I wouldn't say energy momentum tensor does not exist and therefore 3 is not applicable. Rather, I would say that energy momentum tensor is trivial, so therefore 3 is trivial.
So, I mean, usually these things you assume local energy momentum tensor, which realizes the action of the Lorentz symmetries and so on, or whatever.
Well, that's not part of the assumption here. So I don't think this line assumes the existence of. Let me see. Try to. I do not believe that Lorentz symmetry is part of the assumption.
Or whatever space-time symmetries of the energy momentum tensor of the energy momentum. And this the other one, the other concern might be also technical, which is that of the Cauchy surface, which in ADS you don't have, but that may be technical and maybe it doesn't really enter over here.
You are worried that ADS is not globally hyperbolic. You need a boundary condition. Is that your concern?
Yeah.
So let's see. So you're asking. So what? So you're asking whether this set of assumptions, in particular assumption 4, applies to ADS. Is that so? You're asking what happens to this assumption 4?
ADS. Yes.
So what happens to assumption 4 if we are considering ADS? Is that the question?
Yes. Yeah. So 3 and 4 were what I was sort of worried about in this context of the gravitational theory in ADS.
Right. So as I said, my answer to 3 is that it becomes trivial in the gravitational theory because energy momentum. So energy momentum tensor. I would not say energy momentum tensor does not exist. I would say energy momentum tensor is a trivial operator. So therefore, 3 is trivially satisfied. For 4, well, so let's see. So I think that actually we are not using 4 in ADS. We can. Well, let me. I need to think how to properly formulate 4 in ADS. But I'm using 4 for CFT side, but not in ADS side. So there, as I said, there are certainly theories in which 4 does not hold, non-splittable theories. So I need to think carefully how to properly state 4. But whether how we do it, this proof is independent of it because I'm using 4 only for the boundary CFT.
Okay. Yeah. That might well. That's why that might be a more technical thing. But I'm still a little worried about the trigger. I mean, because there is still an ADM mass, or there are global charges associated with the energy momentum.
But those are examples of. So certainly, I'm not excluding asymptotic gauge symmetries, which acts as a global symmetry. So here are examples, and I would say that ADM mass is an example of that. In the case of diffeomorphism symmetry.
I have a question.
Yes, please.
I was just wondering about how important it is to work in a coarse-grained theory. Suppose I really work in the completely microscopic theory, even in the bulk, then would you still
No, yeah, so this argument is not applicable to full quantum gravity theory all the way up to UV. So I'm only making statement about low energy theory. Yeah.
So if I have a better resolution, I'll be able to go around your arguments.
Yeah, so yeah, maybe, yes.
So, a somewhat naive question.
Yes,
So
please.
where is this whole history of the idea that gravity theories have no global symmetry? And you would be tempted to take this argument and use it as a proof that Miller's theorem is not correct. That is the weak link with the
You're saying that so 4 is true. 4 is not true.
4 is not true.
So it's not like so you can have gravitational theory with global symmetry that but the CFT dual.
You have a theory with a global symmetry. You turn on gravity,
Yes.
and somehow the Noether currents are corrected with extra terms that with working lines that go into the other region. Is this a possibility?
Let me see. So, but there is a little bit of mixing up in your argument, if I understand correctly, because
Naive argument.
yeah, but so you're saying that so what I'm using here, the number 4, the split property, is for the dual CFT, and not for the bulk. So you are saying that in the bulk you assume that you have a global symmetry with split property, and then you're gauging it.
So I start out, so there's probably something wrong with this argument, but I'm sorry, I don't know what it is. You start in the bulk with a global symmetry. So this is in the ADS.
Yes.
And then you add gravity to
Yes.
the theory. And the claim is that the gravity modifies the Noether currents by changing them to local momentum. Is this a possibility?
So you are saying that but you are assuming that such construction give you UV complete
Yes.
theory. It is not obvious to me, but
I'm just asking which is really the weak link. So you're highly prejudiced.
I'm highly prejudiced.
Global symmetry is the weak link.
Right. So I'm highly prejudiced, but there are assumptions, and one of the technical assumption is obviously suspect, and so there are certainly quantum field theory without split property. I have a counterexample. So there is such a possibility that there can be gravitational theory with CFT dual, and CFT dual happen to be not splittable. Cannot exclude such a possibility. I do not know of any example. Okay, good. Now you are pressing so much, so let me give you another argument, which I promised, which I'm not going to use it. So then I don't have to worry none of this. So here, so the argument to make use of so the reason I wasn't prepared to present it is that there is.
Could I ask for clarification before you go to the next
Yeah.
argument? I thought you were only using this Noether theorem, as you said, in the quantum field theory.
Right.
So the question of whether Noether theorem is modified by gravity doesn't seem relevant.
Yeah. So I wasn't sure that part of the argument, but certainly a valid question of whether there are global symmetry in gravitational theory that CFTs happen to be not splittable. So that's certainly possible. So,
I'm mystified by the statement that the Noether theory was only used in the time.
so let me give you an argument which has that do not use Noether theory. So if we have low energy gravitational theory with Einstein gravity coupled to matter, there are you can construct as a solution so the multi-leg wormhole. So suppose you have a geometry like this. Okay, each of which are asymptote to ADS. Okay, so now I repeat the argument. So suppose I create some local excitation in the bulk. Okay, and then so suppose there is a symmetry. So there is a symmetry charge, which is charge symmetry acting on here, acting on here, acting on here, and acting on here. So you have a tensor product of conformal fields here in Hilbert space, and clearly there are no direct interaction between conformal field series. These conformal field series are only entangled. So therefore, clearly the symmetry generator is acting as a product of these. So then you can ask what the entanglement weight. So here is the technical part, which actually we need to do a little bit of analysis of the minimum surface, etc. But I can prove that you can arrange solution in such a way that the entanglement weight covers only some region near the boundary, sufficiently far away from this excitation. So that's an argument in which I don't use Neta theorem.
So that argument will tell you that in this kind of bulk geometry, there's no global symmetry. It would tell you that ADS was required.
Well,
But it conjugates what he said.
Yeah, I agree.
Also, doesn't this argument, you're constructing a geometry that kind of has a split property, right?
sorry?
You're using a geometry here that kind of has a split property.
Well, split property should hold for any decomposition of the Cauchy surface. Here I'm saying, so that's sort of idea. So we just need a decomposition of Cauchy surface which excludes this point. So here I gave you decomposition of the Cauchy surface, which is a product of these spaces, which prohibit, whose Ryutaka-Nagi surface does not touch this point. Yes. Yeah.
Sorry, Hiroshi, just to try and understand, we can take this case or the case you have. The bulk operator in the center corresponds to an excitation which cannot be faithfully represented in any one of the CFTs or in any one of the regions, but in some of them.
Yes.
Now, could we try to construct the action of the global symmetry on the bulk operator as follows? We first take the action of the global symmetry in the shaded regions and try to deduce from that how it acts in the CFT in R4 or some of the regions. And then once we have the action in each of the wedges of the CFT, we can define the action on any state in the product.
Okay.
Including the state that would correspond to the bulk excitation. Would your claim be that this action takes you away from the code subspace?
Yeah. So I think that right. So the problem of so I'm not sure I'm answering your question, but the problem of this type of operator is that so in order to construct operator which commute non-trivially, which has a non-trivial algebraic relation with operator here,
Yeah.
you have to have a sort of a superposition of operator like that. So namely that if operator factorizes to subspaces, then for example, I mean there is no entanglement generated between them. So it has to be, it necessarily has to be that operator has to be sum of product of operators of these regions.
The simple product.
So simple product factorized operator is no good. I'm not sure I'm answering your question, but that seems to be criterion. So that the point is that in order to generate a non-trivial entanglement and therefore have non-trivial commutation relation with this operator, so namely in order to have so the point is that this operator acts non-trivially on the code subspace. So in order to have non-trivial commutator with this operator, you have to change the entanglement property, and that is only possible when the operator is not simply a product, but rather sum of products of operators.
So an attempt to construct such an operator which is a simple product.
Right here, yeah.
I mean, to turn that chain around, would it be that if I wrote a simple product operator, I would have to depart from the code subspace?
Yeah, you mean that if this, so you cannot write a local operator in such product form. That's another way of saying it.
So any operator.
So any local operator localized in this kind of region cannot be expressed as products of operator like that.
I see.
Yeah, so that's another way to state
I
it.
see, I see, I see.
It has to be sort of non-trivial sum of product.
Now we see this from the Kaba.
Yeah, Kabat-Lifshitz construction actually explicitly shows that it's actually non-trivial sum of product.
Okay, yeah, sorry, I missed that. And therefore, the action of the symmetry also doesn't translate to a simple product, but
Right.
sum over. But maybe then we define it as a sum over the product. That is.
Yeah, well, you can do it, but symmetry generator is not that. You have to sort of. So this is sort of, that's why property 4 or maybe this one is crucial.
Okay.
It has to be product. So the point is that symmetry is not changing the entanglement property of the code subspace.
Only non-local operators can have non-trivial combinations with this, but symmetry by its nature, by neither theorem, is a local operator.
Right.
That's why it has to be.
So, okay, I was just trying to probe which could be relaxed. So maybe that statement 4 is relaxed as a sum over.
Yeah. So if there are some kind of funny symmetry for which Neta theorem is not true, but symmetry generates a sum of product generating non-trivial entanglement, that may be true. And in fact, I believe that the symmetry generator which changes the phase of 42nd eigenstate is of this type. Okay, so now we are going to miss lunch, so let me skip this. So I just want to say that, well, first of all, the precise definition will enable us to talk about quantum gravity. Now, do you need a dessert?
We need dessert. We have time till 1:30. So
Do you have
it's okay.
do you have stomach for dessert?
Yes.
Certainly. Okay. So let's go to dessert. So now I'm going to prove anything. So here I'm just talk about the conjecture. So there is actually a sort of, in some sense, strengthened version of the no global symmetry theorem called weak gravity conjecture. So it says that in any local low energy effective theory described by Einstein gravity plus Maxwell field plus finite number of matters, if it has a UV completion as a consistent quantum theory, there must be particle with charge Q and mass M such that that this inequality holds. So this is not, so there is actually numerical coefficient, and the coefficient is determined so that Reissner-Norton bound, extremality bound, is satisfied, saturated. So this was formulated by Nima Al-Kani-Hamed and collaborators right after Qumran advocated the Swampland conjecture. And so it's called weak gravity conjecture because if you have such particle, then the gravitational attraction between such particles is weaker than the Coulomb repulsion between them. So therefore, the gravity is weak for such pair of particles. Now, so this is motivated by black hole physics, but even weaker than the argument I gave for the case of no global symmetry. I think to me, strongest sort of argument is based on the fact that in all known construction from string theory, this is true. There is some holographic argument, so if I may take 5 minutes to let me present. So this is actually in the paper by Daniel 3 years ago. So basically he argued that suppose you consider ADS-Schwarzschild geometry. So then the Hilbert space is a tensor product of Hilbert space of conformality theory here and here, non-trivially entangled through one pole. So then you can consider Wilson line. Suppose you have a gauge symmetry in the bulk. You have a Wilson line operator ending on each of these points. So that acts as a charged operator on this side and charged operator on this side. But Hilbert space is tensor product. So that means that if you have if the Hilbert space is tensor product, any operator acting on it should be sum of product of operator acting on each of these Hilbert spaces. So therefore, that means that we should be able to decompose this Wilson line operator as product of operator acting only on this side and acting on this side, only on this side. So how can you do that? You have to cut the Wilson line in the middle. So if you cut the Wilson line in the middle, there must be a charged operator appearing over there, right? So that requires, so you cannot have pure gauge theory in the bulk. You have to have a charged operator in it. But then even if you create pair, if you look at final resolution, then you see there is a problem. So he argues that eventually all the gauge symmetry has to emerge. So he did some experiment, I think, that suppose you have CPN model, and then you have some low energy theory is emergent theory with Maxwell theory coupled to some charged scalar field. And he actually checked that this weak gravity inequality is sort of easily satisfied.
Could he argue for the number?
No, actually, in this case, it's actually sort of widely satisfied. It's actually suppressed by the power of lambda. So it's actually not, I mean, it's not, you cannot check the coefficient in this case.
So this ADS-CFT argument gives you an argument that there must be charged particles, but it doesn't give you an argument for a strong.
No. It's not, doesn't give you saturation. But actually, there is a generalization to it, which actually will appear in my paper with Daniel, where you can actually consider generalization with n, several different number of charges. In that case, actually, Cliff-Chern and Grant-Raymond, a generalization of weak gravity conjecture called the convex Hull condition. So we were able to show that that is actually satisfied in more general. So there is something to this kind of thing. But main thing I wanted to tell you about in this dessert section is that so you have it is often asked, is this inequality needed? So weak gravity conjecture comes with this inequality with equality allowed. The only reason that equality is allowed is that there are examples. So if you have a supersymmetric theory, then sometimes you have BPS particle. BPS particle actually saturates this. So because of this, Kumran and I argue that the conjecture that this is equal only for BPS state, and for other states, strict inequality has to be satisfied. And so this seems like an innocuous generalization or strengthening of weak gravity conjecture, but we found that this leads to some rather surprising consequence. So for example, we show that if this inequality is true, then in any non-supersymmetric ADS supported by flux, there is always some instability mode. So that's bad news for application of ADS-CFT correspondence to condensed matter physics, for example, one might say. So the reason is that, so I assume here that weak gravity conjecture also holds for higher form symmetry, like for branes and things like that. So if you have a flux, so that means that there is a higher form gauge field in the bulk theory. So that means that there must be a brane charged with respect to it. So then if the bulk is supported by flux, what you happen is that it's like a Schrödinger pair creation mechanism. That if you have a flux in the bulk, then you can create pair of charges which can be sort of pair created in the bulk. And so the same thing happens for fluxes. So you can nucleate a brane which eats up the fluxes. But in the case of ADS, actually it's very bad for the following reason. So this is an interesting point, so I want to expand it a little bit. So we say that in flat space or the jitter space, we are willing to live with quasi-stable world. In fact, we ourselves are in quasi-stable existence. But so, for example, suppose there is a instability in our vacuum, and then there is a finite decay probability. But suppose decay probability is very small. The lifetime is much longer than the age of the universe. And suppose something like that happens at 100 million light years away. It takes 100 million years for that news to arrive to us. So we can live happily almost ever after. And the same is true for the zeta space. But interestingly, anti-zeta space, which is supposed to be much more stable than them, is actually really unstable for the following reason. So first of all, as a spatial section of ADS is infinite, and the causal structure is like that. So you have a spatial section, and then there is a boundary to it. And when we talk about the decay probability, what we really mean is a probability per unit volume. So that means that if you consider this section, since this section is infinite volume, so the probability that decay is happening at any point, at one of these points is infinite, or 1. And so, but if decay happens over here, the news approaches to the boundary in finite time on the boundary. So that means that the conformal field theory decays with this time. But actually the situation is even worse because ADS metric has this warp factor. You have dr square plus r square dx square, where x square is coordinate in the spatial direction. As it approaches to the boundary, this r square diverges. So that means that the volume element near the boundary is infinite. So that means that if you have a finite decay probability per unit volume, then the decay can happen near the boundary instantaneously. So usually you introduce some kind of UV cutoff in conformal field theory, which corresponds to IR cutoff in the bulk. So that means that the decay happens with this cutoff time in CFT. But if you have defined CFT with finite cutoff, and if that CFT decays in the cutoff time, well, such theory does not make sense. So that means that if you have ADS with any tiny decay probability, then such theory actually is ill-defined. So actually the situation, so in the case of flat space or the zeta space, you say if you have finite decay probability, well, you have quasi-stable state, but you can still discuss physics in it. But if you have ADS with any tiny decay probability, then that theory does not exist, period. So that's actually that's concern. And in fact, all non-supersymmetric ADS are marginally stable at best, and some of them are unstable in interesting way. So, for example, the typical example is ADS 5 cross S5 divided by discrete symmetry. That was so very impressively, Shamit and Eva pointed this out just within a few months after ADS CFT was proposed. And so this is very important thing. So you start with ADS 5 cross S5 dual to n equal 4 super Yang-Mills. They found that if you divide n equal 4 Yang-Mills theory by gauging some discrete subgroup of R symmetry, that corresponding to considering orbifold of S5 by some corresponding discrete subgroup of SO6, this gamma. They show that if gamma does not fit into SU3, then the supersymmetry is completely broken. Okay? So this was sort of very interesting example of non-supersymmetric holographic duality, except that it doesn't exist. And so the reason is that if gamma has a fixed point, it was shown that there is tachyon in the spectrum which breaks, which violates Brighton-Roller-Friedman bound. And if you have a non-fixed point, then there is the closed string going around, and then that prohibits the tachyon. But then what happens is that you have non-trivial pi1 in the bulk. And if you have non-trivial pi1 in the bulk, and if you do compactification on that, there is a famous paper by Witten that shows that there is an instanton in the bulk in which this S1 shrinks to a point and then disappear and then create the sphere or the whole of nothing. So and then that whole expands at the speed of light and eat up the space. So either case it is unstable.
From the boundary point of view, it's just that the theory is not conformal?
From boundary point of view, it's just a theory does not exist.
In what sense? I can write out a Lagrangian, you mean that it
doesn't have continuum limit, probably.
Because it's not conformal? Because the beta function?
Well, so if you assume ADS CFT correspondence, you can show that the vacuum decay at, so vacuum is unstable in the CFT side. So right. So then that's one way to see. Yeah. So in the first case, what happens is that there's a flat direction. So there's a Coulomb branch, and the Coulomb branch becomes unstable because of the perturbation. So there is no sort of stable ground state in the theory. Yes, that's another way of saying it. So there is an operator in CFT which violates the interactive bound.
But maybe connected to the fact that there isn't a conformal field theory once
So I don't know what happens at the end point of this instability.
Sorry, no, there's two questions. Just one, defining the UV theory, and second, looking at the IR.
Right.
So the UV theory itself does not exist as a conformity because the beta function is not zero. I'm asking.
I'm not sure I can say that.
It's been a while, but I thought that
Beta function should be 0, I think. Yeah, I think beta function is 0.
At one loop, maybe. But then
So let's see. So
properties won't protect you at higher.
right. So they actually so I should go back and read this paper. They give CFT description of exactly what went wrong. This is some kind of perturbation. They describe it as some kind of perturbation to this original n equal 4 theory, maybe double trace operator or something. And then they found that there is no UV fixed point. There is no IR fixed point after you do this.
So the relevant perturbation, there's some relevant deformation.
Yeah, I think they prove that there is no IR fixed point.
It's true that, sorry.
Yeah, please, please.
Just remind me, I think it's true there's some moduli in the bulk which are not stable. Like in the n equals 4 ADS, the dilaton is not fixed, right?
So
in the
that-
bulk. So it's going to acquire potential at some order.
And that's throwing off that.
And that's going to be flowing. So I think that's true. But if I may say, this was the main motivation why, sorry if I can say that we looked with Prithvi, my student, at examples where you stabilize all moduli
Right.
in the bulk.
Oh yeah, so I should have mentioned there. That's right. Sorry.
Yeah, but that was exactly the motivation. So you can actually stabilize in flux compactification
Right.
all moduli, and then break supersymmetry and ask can you get a stable entity.
Yeah. So for that example, I don't have a sort of mechanism like that yet. Yes.
Yeah, but what we found, we looked at all instabilities, and we found there was a large class where there were no instabilities for sure, but there were some instabilities on the edge to the order we could calculate. That is, in ADS, there is some analog of surface tension equals the energy difference between the two vacuum, where the decay is on the edge. And to the order we could work on, we were not sure whether going beyond the approximation.
Yeah, that's right. Yes,
So-
I remember.
So the dilaton was stabilized at what value?
At a control value.
Yeah.
But finite.
Small and finite.
Parametrically small?
Parametrically small.
Parametrically in 1 by f.
In flux. In
One
massive 2A, this is the beauty of massive 2A.
Right.
Sorry, you can you can stabilize moduli with parametric control using the flux. And that's what we did. But there were non-perturbative decays which were on the edge.
Right.
So in particular, at least in leading order 1 by n, you've got a conformity. The line has become a point.
That's right. But as Hiroshi,
And then there's a set, yeah.
It may be e to the minus n, but into infinite volume.
Yeah.
Sure.
So that's what happened.
Right. So yeah. So Sandeep was one of the persons who kindly pointed out this example. After Kumran and I posted papers, there have been several people asking how about this example. So we're able to actually find a new mechanism to destabilize some of them. And so this is an example. For example, Javier Rial and his collaborator pointed out they actually studied compactification, M-theory compactification to ADS5, and they found one example which is non-supersymmetric and stable. All other examples apparently was unstable, but this was only one that was stable without tachyon. The supersymmetry is broken, so this is an interesting example. So they posed me as a challenge, and then so fortunately I had a brilliant Russian student, Lev Spodnienko, and so we worked on this one, and then mostly he worked on this one, and then he came up with a beautiful generalization of Witten's instanton. So the thing about this is that this has no pi 1, but this has pi 2. So we thought that maybe there is a generalization of Witten's instanton where S2 shrinks to a point. And he actually found it in this example.
Sorry, Hiroshi, there's something.
Yeah.
You gave this beautiful argument of the infinite volume in ADS for instantaneous decay. What I'm having trouble understanding is from the conformal field theory why there would ever be an infinite factor.
Well, because the vacuum does not exist, I think.
But I thought it was kind of situation where you had a local stability. It's just that it rolls over. Even the conformal field theory, you had a local stability, but then a
Yes, please.
Let me try to give an argument. In a
Right.
The rate will be
That's
zero
another
or
way of
infinite.
saying. Thank you.
There are only two possibilities.
Thank you.
So if it's non-zero, it's infinite.
That's right. Yeah, I think that's a very
But more
convincing
physically,
argument.
what happens
Thank
is
you.
you nucleate bubbles of all sizes because it's a CFT, and the very small bubbles dominate because they're what
Yeah.
Yeah. And maybe another way of saying it from, I was thinking of a potential that has feature, but that's not consistent with dominator. So like it's pi to the 4 with either positive coefficient or negative coefficient. If it's negative, just rotate. Okay, thank you.
Yeah, I think that's the argument I should have given. Okay, so finally, so this is even more controversial. so there is actually a very interesting paper by Nima and the collaborator where they consider the following thing. Suppose our world is just Einstein gravity coupled to standard model of particle physics. And then suppose for some unknown mechanism, the cosmological constant is tuned to current value in our four-dimensional world. And suppose this is our world. And compactify it on the circle to 3 dimensions, for example. So then there is Casimir energy generated by particle going around this circle. So that modifies cosmological constant. So depending on, for example, so Casimir energy typically contributes more if the particle is lighter. So therefore, actually the resulting cosmological constant, the sign of the resulting cosmological constant depends on whether, depending on the type of neutrino. Okay. And then they pointed out that in the case of Majorana neutrino, you get Anchorita space in 3 dimensions. It's non-supersymmetric. So if we assume that their construction is stable, then it contradicts with our conjecture. So such standard model should not exist. So we propose in this paper that this can be used to rule out certain type of neutrino. And in fact, this was actually taken up by several people, Luis Ibanez and Gary Hsu and other people, and they study. It's still very interesting. And for example, last year, the first paper they wrote, they sharpened it and showed that in the case of Majorana neutrino, you can exclude it in this, and in the case of Dirac neutrino, there is actually a relation they can derive between the neutrino mass to the force and the cosmological constant, which actually is very close to each other. And so it's actually quite interesting. But of course, I mean, here you are assuming that there is a stability. So for example, if you add, so even if this is unstable, if you add particle beyond the standard model of particle physics, and if you take into account the effect of this Casimir energy, so these are massive, so these are corrections, but somehow, sometimes you can make the things stable that way, and or unstable that way. There can be some, you can create some instability mode by adding extra particles. But this is still interesting because that means that this predict what kind of sort of model beyond the standard model exists. So that the criterion is that the model beyond the standard model has to be such that, so if you, for example, know that Majorana neutrino is Majorana, then the model beyond the standard model has to be such that if you compactify the theory on S1, then it becomes unstable. And so that I thought was interesting. So that's sort of more or less what I wanted to say. And but there is one more thing, which is that I'm going to we're going to have a strings conference in Okinawa, and so I'd like to point out that the string theory group here is actually number 4 in the world in terms of the number of people that you guys are sending to the string conference. So we look forward to seeing many of you both at strings conference and perhaps at strings conference a week before.
What is the number if you exclude Japanese groups?
So, in fact, but interestingly, top one, the number 1 group is Harvard, 18. And Princeton plus IAS is 16. And then there comes KK. And then, in fact, Tata Institute and IPMU is tied at 10. So thank you for that. And I look forward to seeing many of you in Okinawa and having fun discussing physics. So thank you very much.
I think we should give
HRI questions.
No question.
That's 1 minute. Well, yeah, we have a question. 1 minute.
Sorry, I have a question.
Please.
You said, I mean, this, so according to the conjecture, one needs the particle which has mass smaller compared to the charge.
Yes, are you talking about weak gravity conjecture? Yes.
Yes. So is this statement independent, I mean, is this RC flow independent statement or?
Yes, so this is an interesting question. I think I have not completely gotten to the bottom of this, but I know Cliff Chen and his collaborator has some interesting work on that. But yeah, so there are various consistency conditions people have been checking. For example, is this consistent with compactification? So suppose you have weak gravity conjecture in d dimension, you can consider compactifying it, and then this relation changes, and is that still compatible with each other? Because you get a relation in d minus 1 dimension, but you also have Reissner-Norton black hole in d minus 1 dimension, and you can compare extremality condition, and that has checked out. And but so RG is another thing because of course these are RG dependent quantities. Yeah, so I think there is a study on that, but I don't remember exactly what the current status is.
Any more questions, Ekarai?
Okay, just following up on that. So is it true that if the correct way to interpret this is in the infrared?
Yes, that's right.
Okay, ICPS questions?
Thank you very much.
Thank you. It was nice hearing from you. Thank you. It's fun.
Wait, Mumbai question.
Let me ask one, sorry,
Yes.
but we can talk later. Which is, so if your interpretation of the weak gravity conjecture extended to higher forms and so on is correct, it also then makes a prediction for CFTs, non-supersymmetric CFTs.
Right.
Namely, they should not exist.
Yes. I should have said it.
Let's say non-supersymmetric conformal theories where the central charge is much bigger,
Right.
is let's say very big, with only a few low-lying operators.
Thank you. Yes. So it's a question to bootstrap people.
Yeah.
Namely that, so there is actually a sort of conjecture that if you have a CFT with large central charge and sparse light spectrum, then this CFT has weakly coupled gravitational dual to it. And so if this assumption is correct, and if this is correct, then that means that such theory without supersymmetry does not exist. So, but then this is something you can check, you can try to check using bootstrap. So because you assume the particle spectrum and you can see whether bootstrap condition is satisfied or not. So yeah, so I should have mentioned it. Thank you for raising it.
So just one quickly about the vacuum stability again.
Yes.
Suppose we had a CFT and S3. Now there is another scalar. And this is not just a pro-man because, typically scalar fields have positive mass because they're an S3. So let's say that conformal theory has a minus pi to the 4, but it has a plus pi square. If there's an n behind that, then this could be very large, logical. It just feels odd to me that you've got your infinity came from the U.
So in that case, R is this one, right?
It came from the UV, but I see. But now by putting it on an S3, don't I more or less stabilize it because I get a potential that looks like this?
Well, at least it decays in one of
Size of the bubble. That's probably
The size of the bubble.
Yeah, it's probably
small, and
then it doesn't matter. That's the entire. Okay, it's probably. Sorry, thank you. Yeah. Okay. More questions?
People are not hungry, it seems.